Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am super happy to have José Rafael and Matias Castro-Tapia with us today. Hello, Rafa. Hello. Goodbye, Matias.
Yeah,
Hi, Frank.
excuse me.
Okay, well, we'll start with you, Rafa. I'll wait for Matias to come back on. And Matias, where are you located at? Or Rafa, where are you located at?
I am located in Boulder, Colorado.
Cool. All right. So, is there still snow in Boulder in April?
No, it's sunny and plenty of mountains and sunlight. Yeah, no,
Lovely.
it's
Lovely, lovely, lovely.
great to be out.
Nice. And it is April 11th, 2024 as we record this. And I'm in Phoenix, and we are definitely warming up into our spring. So we don't have any mountains, but we're definitely warming up. So it's very cool. And Matias, where are you located at?
Yeah, hi. I am in Montreal, so
You probably definitely have snow still.
yeah, yeah. Doing my master in McGill University, but now I'm transferring to the PhD program here.
Oh, very nice.
Yeah, so
congratulations. Well, I look forward to calling you Dr. Matias soon enough. So very nice. Let's see. And Matias, let's start with you. So what do you like to do for research?
sorry, what?
What do you like to do for research?
For research, I mean, for the PhD, I'll be working on white dwarfs.
Okay.
Mostly in cooling on white dwarfs, the evolution of them, crystallization, and that kind of stuff. I have some experience also working on red giant stars. So it's mostly stellar astrophysics, my interest.
Well, it makes sense in Montreal, you would be doing white dwarf cooling. So
yeah. A lot of people working on white dwarfs here.
And Rafa, what do you like to do for research?
Oh, a bunch of things. I like working on compact objects, white dwarfs and neutron stars, and giant planets as well.
Cool. That's a combo.
And more recently, I've been getting interested in helioseismology and solar physics. So yeah, a bunch of things, especially fluid dynamics processes happening in stars and planets.
Sounds like we'll be covering some of that. And so
yeah, maybe.
Yeah, maybe. And so that'll bring us to this very lovely APJ letter. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. A short, intense dynamo at the onset of crystallization in white dwarfs. And Rafa and Matias, take us away.
Yeah, thanks. So first of all, we need to recognize some contribution done by Andrew Cumming. Well, we started this work as a side project when I was a PhD student in Montreal in McGill with Andrew, and then we continue working on that. So part of this were also Andrew's ideas that were further developed by me and Matias later.
Cool.
And something funny to say about this is that when we started to work on this topic, we were not motivated by white dwarf. It was motivated by some compositional convection happening in accreting neutron stars. Which is, in the end, it turns out to be a similar process.
Yes.
Similar to what is happening in white dwarf somehow. So yeah, I think that a good way to start discussing this paper is by talking a little bit about observations.
Okay.
So in that regard, I have to say that we know that there is a fraction of white dwarfs, a few hundred white dwarfs, let's say, that have very strong magnetic fields. If you get the intensity, let's say from Zeeman splitting, you can get magnetic fields of about 10 to the 4 to 10 to the 9 Gauss. So let's say mega Gauss to 1,000 mega Gauss. Okay. And what it is interesting here is that we don't understand well why they have such a strong magnetic fields. And in this paper, we will attempt to explain that. Okay, that is the purpose.
Cool.
So other things that are worth mentioning regarding observations is that it's not clear if the magnetic field is strongly correlated with some properties of the star. For example, if you explore how is the magnetic field as a function of the mass of the white dwarf, you will see that maybe more massive white dwarfs tend to be more magnetic, but there is a lot of scatter in the data. Similarly, you maybe want to compare how the magnetic field behaves with the age of the star, and you maybe see that maybe the older ones have larger magnetic fields.
Okay.
But what is also interesting is that if you compare the magnetic field as a function of the rotation period for the stars that have rotation period measured, you don't see any correlation. It's really hard to see a correlation over that.
Okay.
So there are many things that are hard to understand in this area of magnetic white dwarf. So there are some possibilities that can explain the large intensity of the magnetic field. It could be a fossil field from the progenitor that was amplified, let's say, during the collapse. You conserve magnetic flux, you amplified the field. It could be also induced by a dynamo in some binaries systems. But what really got the attention of people in these recent years is that the magnetic field is created during the evolution of the white dwarf in a process that is called crystallization.
Cool.
So for the people that is going to watch this video, crystallization means basically that the star solidifies from the interior and outwards. And I'm going to explain how that can induce a magnetic field. So imagine that you form a white dwarf, you start with a small core, carbon and oxygen, in some state, let's say liquid. So you have this mixture of carbon and oxygen, and as the star don't have a nuclear reaction, they just cool down over time. And when they cool down sufficiently, what is going to happen is that the Coulomb interaction between the ions becomes important. So especially in the denser regions of the stars, and what is going to happen is that the interior of the star will become a solid. And this solid is going to grow outwards from the center to the external parts of the star.
Cool.
So what is fun here is that as the core solidifies, there is more oxygen in the solid core because oxygen is heavier than carbon. So what happened is that both components solidified, but there is more oxygen. So there is some fraction of the carbon that remains in the liquid state, and since carbon is lighter, it's going to rise. It's buoyant and rise, so it mixes upwards. So basically, what you have is that as the star solidifies, there is a phase separation of the composition, a chemical separation, and the carbon is lighter than the oxygen, and it's just buoyant and moves. It floats. So this is known as a positionally driven convection. It's not thermally driven. It's not because you have fluid that is hotter than the remaining fluid in the surrounding. It floats, it rises because it's lighter.
Yes, I'm with you.
So it's a different way of convection. And actually, since white dwarfs are good conductors, they are degenerate. The conduction is very efficient. Actually, the thermal state in the interior of the white dwarf is subadiabatic. If there is convection, it's not thermally driven; it's compositionally driven. Okay, so that is the point. So this idea of compositionally driven convection to induce a dynamo works in this way. You have these fluid motions going around. You have a conductor, and that means that you have strong currents that are happening within the stars, so that maybe can drive a dynamo. That is the physical idea.
Cool. Okay.
And the usual way of getting a typical magnitude of the magnetic field in this scenario is that it's it's basically doing an equipartition between the magnetic energy density and the kinetic energy density of the convective motions. So basically, as you have here in the introduction, I think it's the third paragraph, you have this equality between b squared over 4 pi and rho u squared. Yeah, right below. Yeah, exactly that. So, so if you have an idea of to estimate the convective velocity, if you have a good model of that, then you can do this and estimate the magnetic field.
Nice.
So that's it.
Sounds
so
simple.
sounds simple. So there is a lot of work done on this actually. To tell you an idea, if you want to measure the velocity, you need to make some assumptions. You need to make some assumptions about how convection will operate. And just to let you know, from the work done until now, different works make different assumptions. So you can get velocities that can go from less than a centimeter per second, okay, to tens of kilometers per second. So it's a huge range of velocities that you can get depending on the assumptions that you made. And of course, that is going to give you a different magnetic field.
Sure.
And the other thing that is worth to note is that this equality that you have here, this equipartition, is not necessarily true. You can probably generate large magnetic field with smaller velocities. You can see that in numerical simulations of other type of stars. So this equality is not guaranteed that it's going to work. Sure. So in this paper, what we propose is that since there is so much, there is a wide range of velocities, and we don't know which one is correct. We attempt to understand or to make a good model for the convective velocities.
Yes.
And calculate in a consistent way the magnetic field without relying on this equipartition or mixing length. Yeah. Right. So that is it. So now Matias is gonna describe some of the cooling models that we use to get an idea of how convection operates in white dwarf, and then we will go over the model that we propose to get the velocity and the magnetic field in a consistent way.
Cool.
So, yeah,
I'm with you.
Yes. Yeah. So an important parameter here to measure the convection or the strength of the convection is the composition flux of like elements that you have during the phase separation.
Okay.
So as a introduction in this paper, we try to describe a bit of the cooling history of massive white dwarfs. In this case, we just put massive white dwarfs, but white dwarfs in general, mostly the carbon-oxygen one. Those that have cores with carbon and oxygen mostly. So we show in figure 1 a model of a 0.9 solar masses white dwarf that we extracted from MESA. So we try to follow the growth of the crystallization curve using the routines available in MESA, principally the new routine of the phase separation written by Bauer 2023. Which follows the chemical separation in carbon-oxygen cores. So every time that you have crystallization, given the Coulomb parameter, you separate the carbon and oxygen, so you enrich the core with oxygen, and you enrich the liquid phase with carbon, which produces this buoyant instability.
Yes.
Yeah. So in the top panel of figure 1, we show basically the history of this crystallization core growing. So we show the mass of the solid core and the radius of the solid core, which they follow kind of a similar behavior of how it grows. But the important thing here to note is the R out that we computed, which is the extent of the convection zone. Okay. And we have two prescriptions for that because the phase separation routine in MESA does a mixing before taking the time steps. So the actual convection that happens in the white dwarf is not followed by this routine. It's just done, let's say, artificially. Okay. Not by the evolution itself. So it has two prescriptions to do this mixing over the star. This is also because the chemical separation is very discontinuous when it happens, so it will somehow broke the running of the code if you put the discontinuity just in the evolution. So that's why people usually decide to do this mixing in standard evolution codes before taking a time step to avoid these numerical issues.
Okay.
So as we can see in the lower panel of this figure, the initial carbon dioxide profile is very flat at the beginning, which is shown with the dotted line.
Okay. Yes.
So if we have a Boolean instability, we expect that the mixing will occur all the way through this flat composition profile because we don't have any composition barrier preventing the mixing.
Right.
But as Rafa mentioned, white dwarfs has very high thermal conductivity, which in principle will reduce the buoyancy. So if we take the Ledoux criterion to mix the unstable part, we won't mix all the way through the flat profile. We will have a very small convection zone at the beginning, and that it will grow. But if we ignore the thermal conductivity, we will have this very let's say enhanced mixing through all the flat profile as we saw in the top panel. So
yeah, actually, can you go to the top panel?
Sure.
Yeah. For example, here, if we take just the purple dotted line, we see that the convection zone grows to the zone where the composition profile is flat, as shown in the lower panel. So it's almost a half of the radius of the white dwarfs. If you see the x-axis of the lower panel.
Yes. Okay, I'm gonna zoom so we can get them both here. Okay.
Yeah. Good. Yeah. So as a bit discussion, this convection zone is not well defined by a 1D model, but we are mostly focused in this case on the composition flux. So we define a parameter called tau in this case that we have described in previous papers in compositional driven convection, which is a measurement of the flux of like elements into the liquid region. Yeah, this tau in figure 2. So in simple words, it's just the thermal time over the pressure sky head over the characteristic time scale of at which we are injecting these light elements in the liquid.
I'm with you. Okay. So you want to take a look at figure 2?
Yeah, please. Yeah, just there, because we defined the flux following the growth of the crystallization core. So we follow the core, the mass and the radius of the core to compute the flux. And we saw that from the models, we expect a transition in this parameter tau, which measures the composition flux. So when we have a value of tau very large, we see efficient convection, but when we have a value less than 1, we enter to the regime of inefficient convection, which is the thermohaline part.
Nice, beautiful. Okay, I'm with you.
Yeah, so some people can wonder, okay, but maybe this is just a numerical thing, because at the beginning of crystallization, the core is very small. We would say yes, but we also did a simple analytical model for tau that shows this discontinuity in the very beginning. And it is because of the very small radius. If you have a very small radius, you will have a very large flux because the surface area where you have the flux is very small.
Yeah, right. Okay.
But the important thing here is that either analytically or from the models, we demonstrate that this efficient part of composition flux just lasts for a few mega years after the the crystallization.
Yeah.
So we can have very efficient convection just for a few megayears after crystallization, and then the thermal conductivity reduces significantly the buoyancy, and we enter into the regime of thermohaline convection, which is less efficient than the other regime. Yeah, I think that's mostly the important part of the history of the cooling of the white dwarf.
Wow.
So just to summarize the idea of section 2, the important parameter here is the flux of like elements that we have, is that what defines the instability and drives convection in white dwarfs, this compositional driven convection.
Yeah. So what we propose is that if stations induce a dynamo, it must happen in the efficient regime where tau is large.
Yes.
That is the point. Yes. So now we will talk a little bit about the model that we made. I promise you like a model to estimate the convective velocity in a consistent way.
Okay.
So as I said, previous authors have done things like this. Some of them use mixed length theory, ignoring rotation and magnetic fields. You can also combine mixed length theory with the flux of gravitational energy released during this chemical separation to get an idea of the velocity.
Yes.
But we follow a different approach.
Okay, cool.
What we did is that we take a balance between the magnetic force, the buoyancy force, and the Coriolis force, which is the equation that you are just showing there. And which can relate the convective velocities with the magnetic field. And through the buoyancy term, this d rho over rho, you can relate that with the composition flux that drive this convection. So if you go down, if you go down, we also use this as a function. You need to make some assumptions about the magnetic energy generation.
Yes.
And what we found is that this paper by Davidson in 2013, they have this nice idea that is supported by numerical simulations, actually, where they claim that the magnetic energy density is set by the work done by the buoyancy force. So so we can combine that assumption that is supported by simulations with our force balance, and we can get the velocity and the magnetic field. So if you go down to equation, I think it's equation 11.
Okay. 8, 9, 10.
So we get an analytic expression from that force balance without assuming anything about the velocity yet. Okay.
Right.
We get this analytic expression for the magnitude of the magnetic field that is induced during the crystallization. And this expression depends on different properties of the star, such as the density, the thermal diffusivity, pressure scale heights, and the rotation period, actually, because we have the Coriolis force, so the rotation periods ended playing a role in this expression.
Yeah.
And you can also see that there is a Peckley number in there.
Yes.
The magnetic field depends on the Peckley number as well. So the Peckley number is just the ratio between the time scale for thermal diffusion and the time scale for convection.
Yes.
So when convection is efficient, the convective turnover time is small, so the Peckley number is large.
Yes.
And when diffusion is important and convection is inefficient, the Peckley number is small.
Yes.
So one of the things that is worth mentioning here is that we explored these solutions in previous work, actually.
Okay.
And what we found is that this transition between inefficient convection and efficient convection that we saw before in figure 1 as a function of tau also happens for the Peckley number. They are related. The Peckley number and tau are related. You can write one in terms of the other. So a separation in tau between the two regimes is also a separation in the Peckley number.
Right.
Okay.
Yes. Okay.
Yeah.
Okay.
So if you go down to equation 11 again, you can see that for typical numbers that you can get, let's say if we use the numbers that we wrote there, the magnitude of the magnetic field that you can get is just 100 Gauss. So there is no way. There is no way that we can explain the observations. We are talking about magnetic fields that are 1 million times larger than this. But again, we should not just evaluate this expression with these numbers, because first we need to know how the Peckling number changed between the two regimes.
Okay.
So that is what we did in section 4. So in section 4, if you go up, the goal of section 4 is that we try to estimate the Peckling number for each regime analytically to get an idea of the numbers.
Yes.
So basically, you can write the composition flux as the equation that is just there in terms of the density, the convective velocity, and the compositional fluctuation that is driving these convective motions.
Yes.
And from that, you can write the Peckling number, which is equation 13. The definition of the Peckling number is the velocity times the length scale of the motion divided by the thermal diffusivity. So it turns out that if you know the flux in the end, if you know the flux or the composition gradient, you can estimate the Peckling number.
Okay.
So the idea of this section is to estimate that flux or this gradient for each regime. So we did that first for the regime of a small Peckling number, so when thermal diffusion matters. So what happens here is that, let's remember that in this process, convection is driven by compositional fluctuations. It's not thermally driven, actually. In fact, the thermal stratification opposes to the instability driven by the composition. Actually, the larger the thermal stratification that you have there, it's going to be harder for convection to occur.
Yes.
So what happened is that in the regime of low Peckling number, diffusion is very efficient. So any thermal gradient that you have that is opposing to this convection is going to get smaller because it's diffusing, right?
Right.
So what happened is that to drive convection in that case, you won't need like a large composition flux, because again, thermal diffusion reduces the stabilizing effect of the thermal gradient. So you need a small composition gradient to drive the convection.
Cool. Okay.
So we estimate that gradient, and it turns out that you can obtain that the composition gradient required to drive convection in that case is just what is demanded by the Leduc's criteria.
Okay.
It's actually very small. Yeah. So if you put that in the definition of the Peckling number in this regime of inefficient convection, you get that the Peckling number is essentially the square root of tau.
Yeah.
Okay? This is square root. This is equation 15.
Right.
So if you go now to figure 2.
Okay. Let's take a look at
figure 2. In the it's that one. So if you go figure 2, then you can see that in the inefficient regime, meaning the white region, this is the inefficient regime, the white region, tau is about 10 to the minus 2, 10 to the minus 1, right? It's very small.
Yes.
So if you take the square root of that, you get a small value of the Peckling number, like 0.3. So if you can go there again to the expression of the Peckling number.
Sure.
Can you go there?
That was 15. Yep.
Yeah, that one. Yeah. So we put the numbers from the cooling models that Matias ran.
Okay.
And we get that the Peckling number is about 0.3 or so, and that is actually consistent with previous estimations done by work done in the early 80s by Mochkovich and late 90s. So that somehow is telling us that we are going into the right direction. Right. But what is good from this analysis is that if you put this Peckling number in equation 11, just our expression for the magnetic field there, let's say it's 0.1, so we get a magnetic field of a few Gauss.
Right.
So it's even worse. So there is no way that the magnetic field can be generated in this thermohaling regime or fingering convection regime. But maybe it's possible in this efficient convection regime.
Right.
So that is what we explore in section 4.2.
Cool.
So the whole point is that to estimate the Peckley number, you need to estimate the composition flux. And then you can plug in the expression in the formulas and solve the problem.
Cool.
So that is the point. Estimate the composition flux. And at the beginning of the crystallization, as Matias mentioned before, the composition flux at the interface that separates the solid liquid boundary is so high that this gradient, this del X here, is much larger than the critical gradient demanded by the Leduc criteria, because convection is very vigorous.
Okay.
So we can, in principle, we can neglect this del X crit and get immediately an expression for the composition gradient, which is what we need to estimate the Peckley number.
Okay.
So if you go down,
Mm-hmm.
you go down
Mm-hmm.
to equation 23. Yeah.
Or 23. Yeah.
So yeah, so we worked out what is the gradient in that regime, and we get equation 23, which give us the Peckley number again as a function of tau to the 5/9, and also proportional to some other parameters here. So we have here the Rayleigh number and the Taylor number. Those are typical parameters that arise when you study convection in fluids. So the bigger the Rayleigh number, the more vigorous convection is going to be. So larger Peckley number, that makes sense.
Yes.
And the Taylor number compares the viscous diffusion with rotation, basically. And what is going to happen is that if the faster rotates the star, the larger the Taylor number is going to be.
Yes.
So yeah, anyway, so the thing is that we can estimate the Peckley number in the two regimes, and in the regime of efficient convection, we get the equation 23.
Cool.
So now that we have the Peckley number, we can just go back to equation 11. We have this expression. We can go back to equation 11 and get an expression for the magnetic field, which is just it's not the one that you just passed. We put the Peckley number in there, and then if you go down, then we get that in equation 24. We get what is the magnetic field in the regime of efficient convection.
Okay, I'm with you.
So what is really neat from this, well, we don't know. Let's say it's too much to say that we solve the problem, but what is really neat here is that if you write the magnetic field in terms of the stellar parameters, you can see that since the Peckley number in the efficient regime depends on the rotation through the Taylor number, you can just rewrite everything just in terms of the star's properties. And the dependence with the rotation period disappears. There is no rotation frequency here. It disappears. So, and that is somehow interesting, because if you look into the data and you plot the magnetic field as a function of the rotation period, you don't see any correlation. You don't see any correlation with the rotation period.
That would be figure 3, right?
No, we don't have the rotation period in this paper. We don't have measurements of that. But you can look in the literature, and there is no clear correlation between the strength of the magnetic field and how fast the star rotates. But maybe you need rotation to drive the dynamo, because you need complex motions.
Yes.
That makes a lot of sense, but it's not necessarily true that you will demand a strict relationship between the strength of the field and the rotation.
Right.
Actually, now that I remember, there is this problem where you plot the activity of some magnetic stars as a function of rotation, and you see that when rotation becomes really fast, there is some point where the activity of the star remains flat. And then as rotation decreases, then it becomes smaller. So there is some sort of saturation going on in those stars, and somehow we are seeing something similar here. Like rotation matters, but there is a point where it saturates and it doesn't play any role.
Right.
Okay. So if you put in the numbers in here, you can see that we can easily explain magnetic fields of the order of omega Gauss. That is a good thing. And the reason for that is because tau is large, and because the Peckley number in this regime, and that is something that I didn't mention, sorry about that, is about 10 to the 6.
Right.
So it's 7 orders of magnitude larger than the Pecklin number that we estimated in the inefficient regime.
Correct.
In the inefficient regime, I think it was 0.1 or 0.3. So now we are getting into the 6. So there is a huge difference. And yeah, we can naturally explain at least mega-Gauss fields with our model. And also, we don't rely on anything about like equipartition or something like that. We made this force balance. We use the assumption done by Davidson in 2013 that relates the buoyancy, the work done by the buoyancy and the magnetic energy, and that's it. We didn't do any equipartition. We naturally solve for both, and we get magnetic fields and velocities that are. I think we get velocities of about 1,000 centimeters per second or so. Yeah, like 1,000 centimeters per second, and that can generate fields of mega-Gauss. We don't need kilometers per second velocities. Yeah, it's crazy. Yeah. So now Matias is gonna show how this. What are the magnetic fields that we can get for different white dwarfs of different masses? And then we will discuss a little bit of what is next and how this relates to the observations.
We'll get to that.
Yeah. Just a few comments before moving to the models. You can see that we made some assumptions either in the inefficient and the efficient regime for the thermal gradients, which are expressed in terms of this gradient X grid. But actually, if you solve from the energy conservation of for the flux conservation of heat, you can obtain the actual values of the gradients, and you obtain the same estimation of the magnetic field that we obtained. It's just if you combine the equations in using the full set for the heat flux and the composition flux, you can get the same estimations that we obtained from these approximations that we assumed from the gradients. It's just we also did in our previous paper in the Castro-Tapia et al. 2024, we mentioned something about how to solve convection given the heat fluxes and the composition fluxes in different regimes. So it's just a short notice. So let's go to the table now and the final figure.
Okay, table. And buoyancy properties.
Yeah, so basically we construct some models with MESA in a very straightforward way. We take the 0.6 solar masses white dwarf that is in the, let's say, in the test suite of MESA, which is one of the examples that you can run easily in models for experimental astrophysics. We take this model with certain composition profile, and we adjust the mass of this white dwarf to generate different white dwarfs of different masses. Some people may wonder why we have ultramassive white dwarfs in this case, but there is some work that propose that you can actually form white dwarfs with carbon-oxygen cores that are ultramassive. By ultramassive, you can refer to those that are more massive than 1 solar masses. Yeah, even 1.3 solar masses. You can even have carbon-oxygen cores. So we run the cooling the models, the cooling. We follow the crystallization as we described in section 2.
Yes.
From during this efficient regime, we computed the buoyancy properties that are summarized in the table. The local in the local region, the local liquid region where we expect the instability, right? We compute the composition flux as we described before, and we just take the numbers and plug into the equation for the magnetic field in the efficient regime, and computed what we show in the last figure. In the blue line is the predicted magnetic field from our Mach balance, and the green points and the pink points are observation from a reduced sample within a volume of 20 parsecs from Bagnolo and Landstreet 2022.
Okay.
We see that we can not like match exactly the data, but the magnetic field that we predict from this mag balance is about of the order of magnitude that we expect. I mean, about a few megagauss. Yeah, so we don't see any relation between the atmosphere composition. For example, here we differentiate between the hydrogen rich and the helium rich. We see a bit of trend for the hydrogen rich, but we cannot certainly say it's exactly a relation.
Well, at least it's not order of magnitude off, so you know.
Yeah, it's just an order of magnitude estimation.
Yeah, it's good. It splits them, so looking good.
Yeah. It's just to make a rough comparison with the data. Obviously, this also point out that probably the dynamo is not the only process that we expect to generate magnetic fields, because even if we have this order of magnetic field generated during the efficient convection, it will last only for a few megayears, as we point out. So the magnetic field will be very in the interior, will be in the very interior of the white dwarf. You have to transport this magnetic field out after the generation of this. So the surface magnetic field that we will expect will be reduced by some order of magnitude than the estimation that we did in this figure. So it's,
radius.
So basically the points are measured at the surface, and what we are predicting, the blue line, is in the deep interior. So before comparing the observation with our prediction, we need to understand first how the magnetic field emerged from the interior to the surface. And actually, that if we can get an idea of that, and if our model is correct, we could only explain everything that is below the blue line.
Yeah.
Because when the field diffuses, it gets weaker. So we can explain some of them, but not all of them. So maybe there is a combination of mechanisms that can give you the whole zoo of magnitudes for the magnetic field.
We'll come back.
Yeah. So this takes us to the point of what comes next, actually. So if you go to the first figure, figure 1, top panel, as Matias mentioned, as Matias mentioned, we don't really know where the boundary, the outer boundary of the convection zone is located. It could be the dotted line, the solid line in purple. So we don't know if the boundary is at, let's say, half of the star's radius, or is constrained to less than 10% of the star radius. So which one is correct? The answer should be somehow in between. We don't really know, because there is no model for MESA that accounts for this mixing at boundaries. It relies on the magnitude of the gradients, where you are going to mix the fluid or not. So that is something that needs to be done. We require numerical simulations to understand, well, where is the boundary between the convection zone and what is on top of that. And this problem is actually quite relevant, because if you want to transport the field, in the right time scale, you want to be closer to the surface. Otherwise, it will take forever to diffuse that field, and we should not be expecting anything. So there must be some mechanism acting here that is helping to transport the field out, because if you just take these molecular diffusivities for magnetic fields and you get the time scale for the emergence of the field, is going to take a long time. We should not be seeing anything. So yeah, that is work in progress, and I think that is the next step. Like understand where is this convective boundary first, and then once we understand that, do the calculation for the emergence of the field and get the right time scale, and see if that is consistent with what we know about the cooling age of the stars. Yeah. So yeah, the message is that we have a natural way of explaining the generation of magnetic fields during the crystallization.
Yes.
That happens. What we propose is that should happen during the first mega years after the onset of the crystallization.
Yes.
And then that field needs to emerge somehow that we don't know yet. But at least half of the problem we kind of understand. Well, half of the problem. There is the other half. Yeah, it's work in progress.
Very cool. Very cool.
Yeah.
Very cool. Rafa, Matias, I want to thank you so much for walking us through your very lovely APJ letter. Very nice.
Thank you. Thank you for inviting us. Yeah.
Yeah. And you kind of touched a little bit there on the theory side of, what's next. Of figuring out how the field gets to the surface. And I'm curious if there are perhaps other avenues available for next steps. Are there plans to do more white dwarf observations and get more B fields from the surfaces of white dwarfs, etc.?
Well, that would be ideal. I'm not probably the samples that we have. It's 20 parsecs, right?
Yeah.
So that is very local.
Very.
So maybe well, clearly the sample of measurements that we have, it's biased. It's not complete.
Yes.
So we need more data to fully understand the distribution, and that of course will motivate new models for this. Yeah, absolutely.
That'd be a call to the observers. More magnetic white dwarfs. More magnetic
white dwarfs, please.
Very cool.
Yeah, and more numerical simulations. Especially, we need people like Evan Anders and other fellows that are doing a lot of work on convective boundary mixing.
Right.
And also how the fingers during the thermohaline convection phase responds to these strong magnetic fields. And for that, we need work from Adrian Fraser, who is an expert on that, and Pascal Garot, too, in Santa Cruz. They are the leading experts on the thermohaline and fingering convection. So we need them to do some work on this.
There's a call out, Pascal. Very cool. Very good. Awesome. Well, I really look forward to seeing this field develop over the next couple of years. It'll be very exciting to see the theory move along, bear some fruit, and in the meantime, hopefully we get a few more magnetic white dwarfs. So it'll be very exciting to see this develop. It's very cool.
Yeah.
Cool. Rafa, Matias, thank you so much once again for walking us through your very lovely article.
Yeah,
thank you.
Thank you for inviting us and giving some visibilities. And sorry if our English was not the best. We are Spanish speakers.
Perfect. Perfect.
Yeah.
Perfect.
A fun fact is that we're both from Chile. We did our undergrad in the same university. And when I was starting my undergrad, Rafa was finishing and starting his PhD at McGill.
Wow.
And when I started here in McGill, my graduate student, he was finishing his PhD.
Somewhere else, yeah.
Small world. Very cool.
Yes.
Small world, yeah.
It's a conservation of flux of Chileans in the...
Yeah.
Well, clearly you should provide an estimate for that, what the flux of and whether that causes magnetic fields or not. I don't know. Very cool. Very cool. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.